Hi, this is Ms. Fitzmaurice, and this video is an explanation of 1995 B1. That's the problem on page 26 of your Unit 5 packet. All right, so in this situation, we have an air track, and basically what that is it's a track, kind of like the ones we have in class, that let you slide something along with almost no friction at all. Think about it as like a physics-centered air hockey table, okay? And we have something that has a speed of, it's like a block or a cart or something, it has a speed of 3 meters per second, okay? And it says this 0.2 kilogram mass, so this mass right here, which is 0.2 kilograms, slides along at 3 meters per second, and it hits and sticks to this other 1.3 kilogram mass. Which is connected to a spring, okay? And we know the spring constant, and we know that the spring is attached to like a wall, okay? So what I want you to do, if you haven't already solved this, is go through and figure out in parts A, B, and C, what idea or equation would you have to use? Okay, so A says, determine the following for the 0.2 kilogram mass immediately before the impact. First of all, we want to know linear momentum. Okay, this might seem too easy, but actually they're just asking you to calculate P equals mv. Okay, second, we want to know its kinetic energy. And this, again, might seem too simple, but all you're supposed to do is find kinetic energy by plugging it into 1/2 mv squared. In part B, you need to determine the following for the combined masses after the impact. Now, the fact that there's a before situation and after situation should tell you that you're either using conservation of energy or conservation of momentum. Because there are two objects, you want to conserve momentum, okay? Remember that when two things crash and stick together, that's an inelastic collision, and in that case, energy is lost. It's not conserved. Okay, so we're going to use conservation of momentum. Okay, so we're going to use sigma p naught equals sigma p. Okay, and then to calculate its kinetic energy, we need to first solve for V and then use K equals 1/2 mv squared. In part C, it says after the collision, the two masses compress the spring as shown. Okay, and we want to know the maximum compression distance. Now we can use conservation of energy, and I'll talk a little bit more about that in a bit. But to calculate the maximum distance of compression, we can use sigma E naught equals sigma E. The before situation is after the impact. So after the two collide and they stick together. The after situation is the maximum compression. Okay, so this spring is squished as much as it can be. So again, if you haven't already, I want you to take this time to actually do the calculations for A, B, and C, and then check back for the answers. Okay, so in part A, all we want to do is find the linear momentum. And so we're going to use P equals mv. We know that P is equal to 0.2 times 3, and so that's 0.6 kilograms times meters per second. Okay, in part 2, it wants the kinetic energy. Okay, again, this is really easy. We're just going to use k equals 1/2 mv squared. Okay, we have k equals 1/2 times 0.2 times 3 squared. Okay, we know 3 squared is 9 times 0.2 is 1.8 times 1/2 is equal to 0.9 joules. Okay, so that was part A, pretty easy. Part B wants us to calculate the momentum after the impact. So my before picture, I have the 1.3 kilograms and it's just sitting there, and the 0.2 is moving towards it with a certain speed. The after picture, those two things are stuck together. Okay, the spring is acting on it, but at the instant that they hit, the spring hasn't been compressed, and so there's not yet an outside force. Okay, and we want to know what is this final velocity. Actually, we want to know what is the momentum of these two. Okay, so we have sigma p naught equals sigma p, and I'm going to call this object A and this object B, and then I'll call this C, this like combined mass. So at the beginning we have PA plus PB. So I'm just adding up their momentums, and that has to equal PC. Okay, PC is what I'm looking for, the combined masses. Okay, I know that at the beginning this guy is not moving, so P naught B has to be 0. Okay, I actually calculated P naught A right here, so that I know that's 0.6 kilograms times meters per second. So my answer is 0.6 kilograms times meters per second. That was only the first part of B, though. In the second part, I want to know what is the kinetic energy. Okay, so I know that PC is equal to 0.6. I also know that PC is equal to the combined mass times the combined velocity. And I need to know this velocity right here in order to plug it into k equals 1/2 mv squared, and particularly it's the combined mass times the combined velocity squared. Okay, so I'm going to go ahead once I find VC and put it in there. Okay, so I have 0.6. I know my mass is 0.2, or sorry, it's not 0.2. The combined mass is 0.2 plus 1.3, so that's 1.5 VC. And I find that VC is equal to 1.4 meters per second. Then I can plug that in. I have K equals 1/2. MC is 1.5 times, sorry, this is 0.4, 0.4 squared. Okay, and when I do that out, I find K is equal to 0.12 joules. Okay, does this make sense? Well, it should be less than the initial kinetic energy, because when these two objects hit each other, they lost energy as heat when they stuck together. And in fact, we had 0.9 joules, now we have only 0.12 joules, so we have lost kinetic energy. That makes sense. Okay, now it says after the collision, the two masses compress the spring as shown, and we want the maximum compression distance. Okay, so we have these two masses, and they are already stuck together. So this is our before picture. Our after picture, they compress the spring as much as it can go. Okay, so, and they're still stuck together. I'm going to use conservation of energy because after the two things have collided, energy will be conserved, okay? After they've collided, there's no heat and no work. Okay, so this is my before picture. In my before picture, these things have kinetic energy. Afterwards, they've compressed the spring, so they only have spring potential energy. Okay, so at the beginning, they have K. At the end, they have US. Now I'm going to plug in my equation, so I have 1/2 mv squared is equal to 1/2 K delta x squared. And I'm looking for this delta x, how much has the spring been squished? Okay, I can go ahead and I can solve for delta x. My 1/2s cancel out, and I find if I do a bunch of algebra, and I'm going to trust that you can do this, but prove it to yourself, that delta x is equal to mv squared over k, all square rooted, which is b, because I can take a v out of the square root, times m over k. Okay, I can now just plug in my numbers. I know that the velocity was 0.4, so I have delta x is 0.4 meters per second times the square root of the combined mass, which was 1.5, divided by k, which was 100 newtons per meter. When I calculate that, I end up with my delta x, and I'm going to write it up here, delta x equals 0.049 meters, which is about 4.9 centimeters, and that's a number that makes physical sense.